Cool. All right, so that was pretty quick. All right, so that's all the questions. And so we'll go to our lesson. Yeah, Alvaro. All right, so let's see here. Oh, before I get into lesson then, just quick thing. So let's hear it. I'm trying to think this way. I'm gonna make sure I keep about 10 minutes left of like me going through all this stuff. So if I'm kind of like at this point, I'm gonna like pause and then kind of go into talk about the pair programming project, which I think almost everyone here, if not everyone, has signed up for. So that's awesome. But it's actually gonna be a little fun thing. It's actually gonna be a Kaggle competition, which is gonna be just for your class. So it's kind of a fun thing. And we'll introduce you guys how to do like Kaggle competitions. And I think it's really useful to, what's it called? Kind of practice with that for the project that you guys are going to do. But you guys will do it as a group and everything. Okay. So I'll keep 10 minutes from on the clock, about like at the like 10 till. Okay. So, all right. So lessons. So we've been talking a whole bunch about linear regression, confidence intervals, stuff like this. Linear regression's the past couple study groups, right? So now I think last time we stopped was basically multicollinearity, right? Is that right? Yeah. Okay. I went that really quickly. Just want to remind you guys, or was it multicollinearity? I'm trying to remember now. I think I showed you guys multiple linear regression at first, right? So I showed you guys all this stuff. Oh, we talked about categorical variables, right? That's what I'm thinking of. So we talked about categorical variables and the multiple ways you can kind of convert over. So yes, we can use categorical variables to do regression. We don't have to have a numeric continuous form. We even talked a little bit about how even if they are numbers, you know, for example, like model year, remember it's like, you know, 70, 71, 72, those can actually sometimes be counted as category as well. It just depends on the context. The main criteria for it being a category versus like a continuous variable, we call it like a numeric variable, is that there isn't as much of a relationship between the increase in the value and like the target factor, right? So especially like, for example, we say like origin is 1, origin 2, origin 3. Does origin 3 really make sense to say it's 3 times as much as origin 1? No, origin 1, 2, and 3 are basically saying what region, you know, or something like that, like where it was originated from. So this is like how we kind of consider like, okay, this is, what's it called? This is a categorical variable. Same thing with cylinders. Like cylinders, you may be able to argue like, oh, more cylinders mean like less miles per gallon. But you wouldn't say like, oh, if we had like 2 cylinders or if we had like, you know, 50 cylinders, like you wouldn't project it further out. Like it really is more of a category of a car versus being like a value that we can tweak and kind of continuously adjust. Okay, that makes sense. Cool. All right. And this is, I think this is one that you guys will probably come across on projects and regression and stuff like that. Is this a category or not? And usually you'll hear me say, I don't know. It could be, you could define it in a lot of different ways and you have to kind of make that decision and honestly what works well. All right. So that kind of ended, I think I stopped there and I basically then said about how multicollinearity. So that's what we'll talk about now. So multicollinearity is basically, well, let me pull up this data. So we're using the auto MPG from the curriculum. And basically the main thing for multicollinearity is basically when things are correlated with each other. So when features are correlated with each other. And this is actually a really important aspect because regression relies on the features to be independent from each other. You can kind of think about this. It's like if we increase one value, we expect this much increase in the target value. But if they're related to each other, right, they're somehow you know, correlated with each other, 2 features, is that, you know, if we increase one, well, this one's automatically going to increase as well, or, you know, could be decrease, you know, could be the opposite correlation. But the important part is like if we increase one, it affects the other one, and then it also affects the target. We can't really tell what's the thing that's making a change, right? And so this is actually really important for regression because basically you might start getting these weird effects where depending on how you view the data or how, you know, how the data is set up, you might have features that are very correlated with each other, which correlate with the target, actually look like they're like 0 and stuff like this. And, or you can double count it. For example, like it's like, oh, it's counting this twice and basically making it twice as much target, where really there should be the same thing. So there's a few things we can do. Just kind of reading my notes here. Regression relies on features to be independent. Yeah, as we change one feature, the others are constant. Yeah, so again, saying like they're independent from each other. So large changes in prediction model from small changes, p-values may be inaccurate. So basically this is the things that come out of multicollinearity. If you have multicollinearity, within your features, these p-values, for example, instead of saying, oh, this is significant, or what's it called? Your coefficients can actually be inaccurate as well. So there are other more methodical ways of dealing with multicollinearity. And I kind of put this like, there's other ways we can do this, and we won't talk about them right now. I'll just tell you guys one common thing that most data scientists will use is something called PCA, Principal Component Analysis. And we'll talk about this in the future. So don't worry about like, like having to use this for the project and stuff like that, but it's good to know because it's very common. And basically what PCA does is that essentially you create new, I call them like super features. It's like you create a little bit of feature, like take a feature from here, and can combine them together in such a way that you create a new feature. So that's me like really hand waving me like, oh, like that's what principal component analysis is. If you're more familiar with like the mathematics, it's basically a projection of the data and basically saying what has the most effect, and you can basically convert your features into a new kind of like super feature. But we'll talk about that in the future too. It's one of those things where I think honestly people say it's very, very complicated. It's like, oh, it's the hardest thing to understand data science. And I don't think actually it's that complicated. I actually think it's a lot easier than people make it out, but that's just me. All right, but let's say we don't use that. So one thing to note first, like before we actually figure out like what to do with multicollinearity, it's good to see like, what does this look like? So I'm using the the auto MPG from the curriculum, since you guys have seen this before. And it's kind of small, but the main thing here is that, remember, we're looking at pair plots here, and I think MPG is not on here. I think I took that out. Yeah, I think I dropped dropped MPG. So these are just the features. And so what we're looking for is basically parts that are correlated with each other. If you see kind of a cloud like this, that's generally a good thing. That means they're essentially random compared to each other. So you can see here, this is weight, and it looks like acceleration. Acceleration and weight seem to be uncorrelated with each other. But you can see a few features already kind of like looking like very correlated to each other. For example, we see horsepower and we see displacement. We see horsepower and weight, they're very correlated together. Acceleration and displacement seem to be a little bit related, but you can see it's a little more like blobby, right? So we can kind of generally see in a very quick glance at this pair plot of like what things tend to be correlated with each other. So to formalize that, right, all we have to do is basically find the correlation factors from these different features. And what's nice is that we can actually use the .core here. And this is super convenient because this just gives us a nice little like 1 through -1. So remember, negative meaning that it's negatively correlated. Like these would be negatively correlated. For example, acceleration seems to go down as horsepower goes up. At least that's what it looks like, right? So those would be negatively correlated, where this right here, weight and horsepower seems to be going up, positively correlated. And you can see there's different factors. For example, of course, cylinders and cylinders correlated 100% with itself, since it's the same exact thing. But we can see, some values like 95%, like 0.95. Then we see some smaller values like 0.29. So you can see that, for example, model year and acceleration don't at least seem to be correlated with each other. Or let's say weight and acceleration, which we saw earlier. So weight, acceleration, we can see -0.5 or 0.4. Yeah, Carl.
So is there like a set number that you want to shoot for when you're looking if something's correlated?
Good question. There's not really a strict number, and you'll hear me say this all the time because it's like, oh, it depends, right? In general, I would say if you have a correlation higher than 0.8, that's probably a good sign of being like, hey, these things are probably too correlated together. And then usually what happens is that you can kind of think it through too. If you have a really high correlation, you can kind of think, why are these correlated? The hard part is that if a feature is a good predictor of the target, and this other feature is also a good predictor of the target by transitive property, you'd expect these two features to be correlated together in some fashion. So usually what I would say is that you look for correlation, you see where this correlation comes from, and you really think about the situation of like, why would this really be correlated together? Does this make sense? Like, is this true? I think, depending if you're like familiar with cars or not, which I know not everyone is. So one classic example is like, there's a data sample or data set that's about advertising dollars. And let's see here, is it advertising dollars? Oh, I'm messing up. But something about advertisement. Or I think it's like sales. I think it's like either sales or advertising dollars, whatever. But there's basically 3 different categories. There's like, oh, you can have how much you have in TV, it's like towards TV advertisement radio advertisement, newspaper advertisement. And in that data set, you actually find that radio and newspaper is actually very correlated with each other. And basically it's like, if you increase newspaper, you also increase radio. Like that's kind of like the relationship. And basically it comes down to like, oh, people who tend to buy advertisements for radio is also going to put advertisements into newspaper as well. Versus like it's not correlated with TV. And those are the kind of things that you might want to like investigate a little bit and like know a little bit about domain knowledge. And then honestly, part of it is trying out, you know, like you can do things like you can try out these features and see, okay, for example, one thing you might see is if you put in, let's see here, if you put in like, let's say a simple linear regression, so like just one feature, one target, right? Unless you do radio versus like, you know, the target, right? It's like how much money or how much advertising total or something like that. And you see like, oh, it does a good job, you know, the p-value is very low. And then you try doing it with newspaper in the target. You also see it does a pretty good job. But then when you put them together, what you might see is that the radio and the newspaper factor, the newspaper would drop down to 0. Like the coefficient is close to 0 and the p-value is very high. And that's because basically it's essentially like being gobbled up by the other feature that explains it because they're correlated together. So it's kind of like double counting. So you kind of like have that. So you might try to play around with it. In general, like I think a good idea is just to kind of have a threshold to begin with. For example, you might say like 0.85 is like really what you want. Like 0.85 is like, okay, anything above 0.85, investigate, maybe consider dropping it. And you might try multiple models and see how well it does. And this is of course, like you can imagine, this can be actually very taxing, like how much work you put into this too. So it's also really useful to understand it from like a domain side. It's like, okay, why would these be correlated or just pure chance? And basically you can go off of that. And the short solution to this, like, this is why I'm kind of like, oh, it's kind of depends and stuff like this, because if you do some more advanced techniques like PCA will get rid of most of this this issue. But since we don't have PCA right now, one solution essentially is just to drop, basically don't use one of those features. Like say, like, okay, like we don't need to double count essentially on this correlated feature. So that would be kind of like the way you go about it. But as a general, like, I mean, everyone has slightly different ones. I've heard people say 0.7 is too high. Other people, I've heard people say like, oh, 0.9, you know, is really as high as you can go. I would probably go around, I personally would probably say 0.8, 0.85 would make me suspicious and see if it works. So yeah, that's kind of my fuzzy, you know, this is what the fun part of the modeling is. It's all very fuzzy and there's all these different things you can do. Yeah, does that kind of answer people's questions? Thumbs up, thumbs down. Okay, cool. All right, and then I just really quickly, as I was talking, I just did the heat map here of the correlation. So this correlation is 1 for 0, which, you know, I don't know about you guys, but numbers just like, just a bunch of numbers on here. Usually it's easier to kind of see from color. So you can see here that basically the lighter it is, the higher the correlation factor is. Okay, so this can be useful to just very quickly look at it. Okay, cool. But solution basically is you drop it, like you drop out one of those factors. You might try to do multiple models, trying like 2 or 3 models of trying to drop out some of these correlation factors. If you're using stats models and you're doing p-value, for example, you can see if they're correlated together, or not correlated together, but you can see if the p-value is very high, then it might be suggesting that you should drop out that factor. And that's probably because of multicollinearity too. Okay.